Welcome, viewer, to our presentation on Project 6's robotic arm control system. Our senior design entails designing a robotic arm control system for the Oregon State University Robotics Club Mars Rover project. This project has an arm on it which will operate as a spherical or in a spherical system, but must be controlled in a simpler Cartesian or cylindrical system. So the challenge posed to us is to design a control system for this robotic arm. Everything from the motor drivers to the servo controller to the control system for every electronic piece on the arm to the software and inverse kinematics that will allow this arm to be controlled easily from a user's perspective. We are the group members. My name is Ben Porter.
Frank Coleman.
I'm Bradford Didbell.
In our presentation, we'll begin with an overview of our system, starting with the main block diagram, and going on to talk about the servo controller, the motor controller, the sensor interface, and the other various components of our system in more detail.
First, we're going to talk about the overall system. I'm going to go over the top-level block diagram for our senior design project. It centers around the main controller, which is the central communication hub for the system. It's the component that talks to the rover. It receives the commands from the rover and routes them to the various subsystems. There are three subsystems. The motor controllers, which drive the motors on the arm. The servo controller, which controls a chain of AX12 servos that control the end effector. And the sensor interface, which interfaces and reads the sensors for the science tasks. I'm going to talk about the servo controller subsystem. The servo controller is an embedded circuit that monitors and controls a chain of AX12 servos, and these servos control the position and orientation of the end effector. It receives instructions from the main controller over an RS-485 link, and the differential serial data transferred on this link is fairly noise immune. The servo controller then takes this data and translates it into coordinated motion of the AX12 servos. It communicates with the servos over a TTL UART link, which is susceptible to noise from nearby power electronics. And the way we dealt with this noise is by adding a low-pass filter on the input UART, followed by a Schmitt trigger with 1 volt of hysteresis. So all signals below -13 decibels are blocked.
Alright, now I'm going to discuss the motor controller component of our top-level block diagram in more detail. The specifications for our motor controller are to drive a 24-volt DC brushed motor at currents up to 5 amps continuously. Our implementation is fairly simple. We started off with a H-bridge design. This is a final product. You can see the H-bridge on the bottom here. And in combination with the simple H-bridge design, we also employed some specific features which make the motor driver more functional for our specific purposes. One of the most important features that we employed with this motor driver is the ability to read in a 13-bit magnetic encoder. So we have a synchronous serial interface that interfaces to the magnetic encoder and reads back the position with 13 bits of precision so that we can close the loop on a position control loop. In combination with that, we also have a velocity control loop. Most velocity control loops for motor drivers require the use of an encoder, similar to this one, where there is an open hole and a closed hole which will interrupt the photodiode/receiver pair and give you some sort of pulsed output. And you can use that pulsed output as far as the frequency to determine the speed of the motor. In our case, we couldn't access the output shafts of our motors directly, so in this particular motor the output shaft is right on the back of it. Our motors were all enclosed in a metal housing and we couldn't get to this output shaft, so we had to come up with a different solution. Our solution was to essentially apply a negative resistance on the output of our motor driver to cancel out the positive resistance inside of the motor. The way this works is this. So a general motor, DC motor model, is a voltage source in series with the resistance of the coils. The voltage source is proportional to the speed of the motor by some voltage proportionality constant. And if you apply a voltage to this voltage source of a specific amount, the motor will rotate at a specific speed, regardless of load. Unfortunately, if you apply voltage here, then as you increase load, increased current goes across the resistor, and by Ohm's law, there's a voltage drop across this resistor, reducing the voltage and the speed of the motor. But if you can apply negative resistance to cancel out positive resistance of the motor, then you can essentially have on the terminals of the ideal battery in the motor the same voltage that you apply out here. Our motor driver accomplishes this by measuring the current flowing into the motor and adjusting the output voltage correspondingly.
Alright, so I'll be talking about the sensor interface block. The sensor interface is responsible for reading data in from sensors and transmitting that data back to the rover over an RS-485 interface. The sensor is designed to measure the resistance of the soil from a range from 1 to 100 megaohms. It is also going to measure the magnetic permeability of the soil. The magnetic permeability sensor charges and discharges an air core inductor. Now, the frequency will change as the permeability of the material near the sensor increases the inductance. To measure the resistance of the soil, we utilize the circuit shown behind me. This is represented the probe that we will put into the soil and measure the soil resistivity, which is on the order of megaohms. We'll utilize 3 MOSFETs here connected to a 1 megaohm, 10 megaohm, and 100 megaohm resistor. You can choose between which value most closely matches the resistance of the soil. That will then be fed into our op-amp here, so the unity gain op-amp, to act as a buffer before we send that data to the analog to digital converter and then onto the microcontroller, which will then communicate with the rover.
Here is our final product demonstration. So as you can see here, we have the arm attached to the 2011 University rover, and over here we have the interface for the rover, which will be running at the base station, currently running the firmware for the software for the arm. On here you see an OpenGL drawing of the arm. This drawing matches exactly the configuration that the arm currently has. If we can get a perspective view of the arm from the side, you'll see that it matched the view of the drawing pretty closely. Now, the arm is currently being controlled by a PlayStation 2-like controller, and it is operating in a Cartesian system. So if I push this joystick up, the arm moves directly up, the end effector will. If I push this one down, it moves directly down, and to the left, to the right, and in and out. And you can also close the gripper and open the gripper and all the other sorts of functionality. So I'll demonstrate the arm pushing a button on the panel first. So let's prepare the button. And this is one of the competition tasks that we may run into in Utah. There'll be a panel similar to this which has a variety of different switches and buttons on it. We'll have to flip switches and press buttons and plug in plugs in a specific order. So I can push buttons easily. Let's see it flip a switch. Again, the Cartesian system that it's operating in makes operation much easier than if you had to control every joint independently, as if you were to have a spherical system. So switch is on, switch is off. And the design of the end effector allows easy gripping of a standard NEMA 5 household plug. So I'll grab this plug and pull it out and plug it into a different socket. In review of our senior project this year, we have some helpful hints for seniors next year that you should probably pay attention to. Personally, this is a very complicated system from a student's perspective. We have motor controllers, main controller board, our servo controller board, and a bunch of wiring and a whole bunch of other stuff going on in here. It just, in short, takes a long time to get it all working together. So one of the best pieces of advice that I could give to a new senior is to choose a simple project. Don't choose something as complicated as this unless you really have time to dedicate to it. Frank will now offer some advice.
So start early and work hard.
And now Brad.
I'd say meet often as much as you can. If you have any circuit boards that you wanted to implement, then order those soon.
Yeah, great advice. Thank you for watching, and I hope you enjoyed this video.